Okay, guys, so good morning. Hopefully you had a good Monday and that everything went well. Looked like you guys did pretty well on the approximations with tangent lines. Looked like that went pretty well in general. We feel pretty good about that. Thumbs up. Approximations with tangent lines, what we did yesterday. Looks like some of you got a good head start on the quest for that also. The quest is really short, so if that's still fresh in your mind, I would recommend doing it. I think that one's due Wednesday or Thursday. I would just try to get that done as soon as possible because the stuff we're going to do today and kind of for the rest of the week is called optimization, and it's a little more challenging. So if you felt good about the separable, or I'm sorry, the approximations with different approximations using differentials or tangent lines, I'd recommend doing that quest. We're going to jump right into optimization. Okay, so let me go ahead and share my screen. Nope, that's not what I wanted to do. There we go. Okay, this is a big topic. This comes up quite frequently in both sections. It's a little bit challenging. Kind of like related rates was a little bit challenging. There were some really important steps. They don't really give you the equation. It's not so straightforward of a question. You kind of have to come up with the process here. I think it'd be helpful to write some of these things down in your notes regarding optimization. In your Princeton review, if you're trying to look up examples, they're called applied maximum or minimum problems. So that's the other thing. Most often these are referred to as optimization if you were to search on YouTube or something, but they're also called applied max and min problems. So the first thing we're going to do is determine the primary equation. I will explain what that is. We want to determine the thing we are trying to maximize or minimize. Okay, so our primary equation is like, what is the thing you want to find the most of or the least of? So that's our primary equation. And then we're going to determine our constraints. So usually you're given additional information that limits you. So it says something like the area must be 24, but find the max volume or something like that. And so we have some constraints that we're given. What we're going to do is we're going to plug those constraints into our primary equation and simplify. Often if you don't simplify, or if you don't plug your constraints in, first of all, you're going to get wrong answers. You're not going to have enough information, but it's also going to make the derivative harder. So always plug your constraints into your primary equation and simplify. And then the next thing we're doing, since we're finding maxes and mins, is we're going to take the derivative and set it equal to 0. And the thing you're taking the derivative of is the primary equation, because remember, the primary equation is the thing you're trying to maximize or minimize. So you want to take the derivative of the thing you're trying to find the max or the min of and set that equal to 0, just like we do in a lot of normal problems. And then you're going to solve. Sometimes the thing that you solve for from that derivative is not what the question is asking for. So make sure you always go back and read the question so that you're actually solving for what they're asking. And then often in these kinds of problems, there's units. So just make sure that units are included. Okay, so I'll come back to this slide quite frequently. If you just have even like the colorful stuff written down, that will be helpful. Like primary equation constraints, plug constraints into the primary, take the derivative, set equal to 0, solve. Okay, so here's our first example. You don't need to write all of this down. I am recording this, so I'll throw this up on YouTube later. So it says a rectangular field bounded on one side by a building is to be fenced in on the other 3 sides. Okay, so we have a rectangular field bounded on one side by a building is to be fenced in on the other 3 sides. Often a picture is going to be really helpful before we even go any further. So we have a building. Here's my building. And the idea here is that I have a fence coming out of this building. And it's a rectangular fence, but there's only 3 sides because it's boxed on one side by the building, right? So I don't need a fence on the side touching the building. The building is the thing that's enclosing that portion. But I have another 3 sides of this fence, and it tells us it's a rectangle. So I'm off the bat going to label that my horizontal component is X and my vertical component is Y. And you'll notice I have a Y on this side too. All right, so that's my fence. It says if 1,000 feet of fence is to be used, Find the dimensions of the largest field that can be fenced in. Okay, so we're looking for the largest field. The thing we need to determine is what our primary equation is. And I often label it as primary, so I know what the primary thing is. So if I'm looking for the largest field, what am I trying to maximize in this case?
The area.
The area. I'm trying to maximize the area of that field, right? That's the thing I'm trying to maximize. So I want to write down my primary equation as area equals, and then what would the area be in this case, Gus?
X times y.
X times y, perfect. Okay, now I don't want to take the derivative of this yet. I don't want to take the derivative. I also need to figure out what my constraints are. Okay, so my constraints is any other information in the problem or anything that's limiting me, right? So it says 1,000 feet of fence is to be used. That is my constraint. How would I write that into an equation? Because I want to come up with an equation. Anybody?
2y.
2y equals 1,000.
So 2y plus x equals 1,000, right? So it's saying that my perimeter, the amount of fence I have, which is y plus x plus y, has to equal 1,000. So if we simplified that, we get 2y plus x equals 1,000. Okay, so that's my first two steps. I identified my primary. I identified my constraints, right? The next thing I want to do is I want to take those constraints and plug them into my primary. There's a couple different ways you could do this, right? Often it's helpful to isolate a variable in your constraints and then substitute that into your primary. So I'm going to isolate the x just because it's the easiest thing to isolate here. So if I isolate x, I end up getting 1,000 minus 2y is equal to x. I haven't really done anything, just moved the constraint around. Okay, now what I'm going to do is I'm going to take that constraint and I'm going to plug it into my primary equation. So that's going to give me area is equal, my x is now technically equal to 1,000 minus 2y, and then I'm still multiplying that by y from my primary equation. Identified my primary, identified my constraint, plugged my constraint into my primary. Okay, now I still don't want to take the derivative yet because as it's written, I would need to use product rule in order to take the derivative. Okay, I've gotten rid of a variable, so that's a lot easier because now I could just take a derivative with respect to y instead of taking it with respect to different variables. But it's helpful to simplify this before you take a derivative. So we're going to simplify my primary equation by distributing that y. So we get 1,000y minus 2y squared. Now here is a really common mistake. Students often will set this equation equal to 0, which is not what you should be doing. All you would be doing is saying that the area is equal to 0 if you do that. Instead of setting this equal to 0, you still need to take the derivative. So don't forget to actually find the derivative of this equation, right? This is now the thing I'm trying to maximize. I'm trying to find the maximum area. So I want to take the derivative and I want to set that equal to 0. Okay, so I'll take the derivative of this. I'm going to just call that a prime. And now some students get confused, like what am I taking it with respect to? Am I taking it with respect to time? Well, if you only have one variable in here and you're trying to find the maximum of this function, you just take it with respect to that variable. So I don't have to do any implicit differentiation either. Okay, so my derivative of 1,000y is just 1,000. My derivative of 2y squared minus 4y. Okay, now I have to set this equal to 0. So I found my derivative. I'm going to set that derivative equal to 0. I get 0 equals 1,000 minus 4y, add the 4y over, divide by 4, y is equal to 250. Common mistake, students box this, move on. That's not what the question asked for. It wanted us to find the dimensions of the largest field that can be fenced in. Okay, so I know what y is now. I know y is 250. How do I find x? Anybody have an idea? How do I find x?
plug it into the constraint.
Plug it back into the constraint. So this constraint had information relating X and Y, and it was equal to a value, right? So I'm going to be able to find what X is if I plug it back into my constraint. Even better, use the thing that you isolated. Often you're going to isolate the variable that you're needing, right, in your constraint. So you don't have to go back to the original constraint equation. You can use the one we manipulated in order to solve for X, because that's what I now need to find. So we're going to take this. We get X equals 1,000 minus 2 times 250 equals 1,000 minus 500 equals 500. So we now have our X and our Y. Again, students will box this, they'll box this, and they'll move on. Not what the question asked for. The question asked for the dimensions. So it wants the dimensions of this. So how would you write that answer? Someone I haven't heard from yet today. What do you think you'd write? Only people I've heard from know how to write dimensions? Come on. I believe in you.
500 feet by 250 feet.
Yeah, so 500 by 250 is part of it. And what both of you said was correct. You included the feet. So you need to have units in there also. You can't just put units at the end. You need units for each part. So 500 feet by 250 feet or 250 by 500. We're not sure what the orientation of the field is, so it's fine either way if you put 500 feet by 250 feet or vice versa. Okay, any questions on this problem?
What happens
Now,
if the building is...
Sorry, go ahead.
Well, like, why do we put the building on the X side? What happens if it would be the same if it was on the Y side?
Yeah, you get the same thing, you just get different dimensions. Like your X might be 500 and your Y might be, or your X might be 250 and your Y might be 500, but it's irrelevant. Because all we're saying is one side of the fence is 250 and one side of the fence is 500. Now, a different thing they might ask in order to figure out, like, well, is the 500 on there twice or is the 250 on there twice? They might ask that in a different way. Like, two sides of the fence are this length. One side of the fence is this length. But the way the question is worded, it asks for dimensions. This is how you'd write that answer. Good question. Other questions? Okay, I did start off with kind of an easy one. They do get harder, but hopefully we're understanding the process. So again, the process, identify the primary equation, identify the constraints, plug your constraints into your primary equation, simplify, then take the derivative and set it equal to 0, and then solve for whatever the question is actually asking. Okay, let's do the next one. This one says a manufacturer wants to design an open box. Open is important. It's really important you read these questions carefully because that word open changes a bunch of stuff about this problem. Okay, so a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. Notice it tells us it's a square base. It does not tell us it's a cube as far as this box goes. A box is not the same as a cube. Okay, so it tells us we have a square base. It does not tell us that we have a box or that we have a cube, excuse me. Okay, why am I clarifying that? What's the difference?
Well, you'd have a different primary equation.
We'd have a different primary equation. I'm specifically clarifying that the dimensions of the base are square, right? So I have a square base. But the height of this is not necessarily the same as that base. So that's an important thing to identify, okay? What dimensions will produce a box with the maximum volume? Okay, so let's think about this situation. I've got a square base, call that this, okay? And I have a box here. And the idea is it's open. That doesn't mean I have like sides coming out. We're not like looking at an Amazon box or something here. The idea here is that there are 5 sides to this box instead of 6. Okay, so I've got the sides, 1, 2, 3, 4, and the base, 5. I have 5 sides on that. I don't have a top. Okay, so we're just missing the 6th side. Okay, that's the idea so far. I have a surface area of 108 square inches. and I want to produce a box with the maximum volume. I would like you to try to write down your primary equation and your constraint. And we're going to go into small groups to talk about this. Okay, so primary equation and constraints, you need to know what this question says. You need to make sure you have that 108 written down. Only going to give you a minute or so in your small groups. I just want you to write down the primary and the constraints. I'll call you back pretty quick. You guys are the only group that has it. All right, I think everybody is back now. We only had one group come back early, so I'm wondering how we did. Let's go to Ethan Balliser. Ethan, why don't you tell me what your group got for your primary equation?
Our group got something different, but
Oh, well, that's great. Why'd you guys come back?
Well, because I didn't read the last part of the question.
Oh, Lord have mercy. Okay, so pause really quick. Let's make sure we're all on the same page. Yeah. What I sent out as a message was that we're going to call the base B. So those sides of that base are going to each be called B, and then the height is going to be called H, just so that we're all on the same page. It doesn't really matter if you call it X or Y, but I just want all of us to be solving for the same thing right now. Okay, so if we're trying to produce a box with the maximum volume, what thing am I trying to maximize, Ethan?
You're trying to maximize your base and your height.
Not necessarily. It's in the question. What thing am I trying to maximize?
Your surface area.
Okay. Box with the maximum volume.
Oh yeah, your volume. You're trying to maximize.
Okay, I'm trying to maximize the volume. Okay, I'm trying to find the maximum volume. So my primary equation needs to be a volume equation. Mm-hmm. Okay, it might help to maximize a base or a height or a surface area, but we want to for sure find the maximum volume. That's what the question says. What would the volume of this box be equal to, Ethan?
B squared times H.
B squared times H, perfect. So that is my primary equation. I'll let you off the hook. Let's go to Charlie Fallon. Charlie, what is my constraint here?
Your constraint is that the one side of the base, like b squared, has to equal 108.
Okay, so not quite. It said the whole surface area of the box. So I've got this side of the box, I've got this side of the box, I've got the back side, I've got this side, and I've got the bottom.
Okay, sorry, I thought it meant just the base. So
nope,
would it
yeah,
be
so the surface area of the box, this is where the fact that it's an open box makes a difference because there's 5 total sides. Now 4 of those sides are exactly the same, right? It's an H times a B.
Right.
Right? So that's on 4 sides of this. And then on the bottom, I have a B times a B. So my
would it be
total surface area, 4, go ahead.
4HB plus B squared?
And what's that have to be equal to?
108.
Perfect. Okay, so these are visual. Like that equation is not something you just know off the top of your head. You have to really work with the picture, visualize, make sure you're reading it correctly, because otherwise if you misread it, you might put 4BH plus 2B squared. But the fact that it's an open box is what makes the difference there. Some people might accidentally read a box as the same as a cube, so they might put for the volume B cubed, or for the constraint 4B squared or 5B squared or something like that, right? It's important you know that the height and the base are not necessarily equal to each other. Okay, from here, this is my primary, this is my constraint. The next thing I want to do is plug my constraint into my primary. To do that, I should move something around in my constraint, or maybe move a couple things around. Take a second, see if you can manipulate your constraint to isolate one variable. It's helpful to isolate one variable in your constraint. See if you can move it around to do that. I'm going to call on someone in just a second. Nathan Wise, how did you isolate a variable in your constraint?
Could you just subtract, I'm not sure if this works, but could you just subtract or remove over 4BH and then keep the B squared and plug that in?
So no, because you still would have 2 variables, because you still would have a B and an H. The whole idea is to get rid of a variable. So could you plug it in? Sure, but you're still going to have 2 variables on that V equals equation. You're going to still have a B and an H. Our goal in simplifying that primary equation is to get rid of a variable. That's why we want to isolate one variable in our constraint. Okay, so it'd be easier just to move the 4BH over. That's not the thing we're going to isolate. So we're not going to try to isolate B squared. Okay, what else could you do, Nathan?
Isolate the H.
Isolate the H, right? So I could subtract the B squared, and then I would have 4BH is equal to 108 minus B squared. And then I would divide by 4B and divide by 4B. Now we have H equals. We've totally isolated H, which is going to allow me to get rid of H in our primary equation. Okay, you can simplify this as much as possible. So yes, you could leave it as like 108 minus B squared over 4B and go ahead and plug that in. Or you could start simplifying things about this, right? So 108 divided by 4 is what, 27? So that would be like a 27 over a B minus a B squared over a B is a B, so B over 4. I think that's right, right? Yeah. Good. And then you can plug this in. So again, you could either plug this one in for H, or if you prefer, you can plug this simplified version in for H. Okay, there's a couple more steps. I'm going to send you back to your small groups for a few minutes. I want you in your small groups to substitute in your constraint into your primary. Simplify that equation as much as possible. So that if that's distribute or simplify into a power function if you can, then you're going to take the derivative, set it equal to 0 and solve, and then try to answer the question being asked. So I'm going to give you a few minutes in your small groups. Are there any questions before I send you off? Make sure everybody is unmuted and that you are working together so that everybody comes back with the same information. Help each other out. Ask questions if you have them. This is a hard chapter, so ask those questions. Okay, rooms are open now. I'll see you in a few.
I accidentally clicked to go back.
I was like, Luis, you're the only one from your group that's back.
Yeah, my bad.
Did you guys make some progress, Luis?
I mean, yeah, I guess they kind of did, but since I was late, I kind of don't understand kind of what they're saying, so.
Okay, I've recorded it, so it'll be posted later.
Okay, thank you.
Mm-hmm.
Ms. Toshner,
Yes, sir.
I have a quick question just based on this this whole problem.
Yeah.
How do we know that it is the top side that's an open box? How do we know it's not like one of the four like one of the four BHs essentially?
That's a good question. I think that's what an open box would indicate, that it would be open on the top. I think that's kind of an assumed thing, like the base is the opposite side. College Board is a lot better at being extremely clear. So they would say like a missing top side or something like that. Like College Board is very clear. This is just a problem that I found in one of my textbooks. So that's where it's probably not as clear as College Board is. That's a good question. But yeah, we would assume the most like basic scenario, open generally means the top is missing. Good question. Okay. Did we make some progress? Thumbs up. Yeah, feeling okay with this? Let's go to Mateo. Mateo, what did you do from here?
So I plugged H into the primary equation, which gave me V equals B squared times 27 over B minus B over 4. And then
okay, what'd you do from here?
If you simplify that, you get V equals 27B minus B cubed over 4.
Okay, from here, what'd you do?
And then from there, you can use the power rule to get V prime equals 27 minus 3/4 B squared.
Yeah, because that divide by 4 doesn't mean we need quotient rule, right? A divide by 4 is the same as times 1/4. So if it's helpful, write it as 1/4 B cubed, just so that you can see that. So then we get a 3/4 B squared. Okay, keep going.
And then you set that equal to 0.
Okay, from here?
Then I added the 3/4 B squared to both sides. So you get 27 equals 3/4 B squared. And then divide or multiply by 4 on both sides and divide by 3, which gives you
Okay, so
B
here, really quick, I just want to pause. Some of you at this point will grab a calculator, which is silly, or you'll start thinking about what 27 times 4 is, which isn't that hard. But the easier thing to do, in my opinion, is to do the 27 divided by 3 first, which you're allowed to do, right? 27 divided by 3 is just 9. 9 times 4 is 36. Think about it that way if you can. This would definitely be a no calculator problem. So don't get tripped up on that math if there's easier ways to do it. So we get B squared equals 36. So we would technically get B equals a plus or a minus 6. Mateo, why does only the plus 6 make sense?
Because you can't have like a negative measurement.
Yeah, we can't have a negative dimension. So sometimes negatives will make sense in the problem. In this problem, it doesn't really make sense. So we get B equals 6. Now, that's not our final answer, right? We needed that to find our final answer. What do I do next, Noah?
You need to plug B back into the constraint equation. Or I guess B squared, you could do B squared because that was given already.
Yeah, so we could either plug B squared back into the constraint equation or B back into the constraint equation. So what did you do from here?
So I plugged in B. So going to the constraint equation, I isolated H.
Okay.
So H equals 108 minus B squared over 4B. And then plug B. So
H would equal 108 minus 36 over 24. And then 72 over 24 is 3.
Okay, so how did you write your final answer? I agree, now we have B, now we have H equals 3,
Yeah.
right? That's not what this question asked for. It asked for what?
All the dimensions.
Okay, so how would you write that as a final answer?
6 inches by 6 inches by 3 inches.
Perfect. And be careful, right? We have our base twice. So if you just wrote 6 by 3, that's not a volume. We have a box here. We have 3 total sides of this box. We have a base that appears twice because it's a square base. And then we have a separate height. So we get 6 by 6 by 3. And yes, you need inches on each part of that, not inches just on the end. Make sure you remember your units. Okay, any questions on this one? Okay, let's go on if there's no questions. No questions at all? Awesome. Okay, let's go on. So this one says, what is the radius? So maybe in your work, just write radius question mark. That way you know what you're finding, because I'm going to send you for small groups for a big portion of this one. Okay, of a cylindrical soda can. So we're dealing with a cylinder, just like a normal soda can, with a volume of 512 cubic inches that will use the minimum material. So I want the minimum material used. So I have a tin can, I'm trying to use like the least amount of aluminum there, okay? I have a volume that is equal to 512. They would not probably give you any equations for this, even on College Board. They would expect you to know these. So I want to talk through just cylinders come up quite frequently. You need to know some information about the geometry of a cylinder, okay? For the volume of a cylinder, the volume is just equal to the area of the base times the height. Now the base of a cylinder is a circle, right? So all you're doing is the area of a circle times the height. That's how you find the volume of a cylinder. So that means our volume is pi r squared h. Okay, now the surface area that we're also going to need in this equation, I'm going to just call area. So we just have one variable there. We're not going to use like SA, just use one variable. So area makes the most sense. I've got the whole outside of the can, and then I have the top and the bottom of the can, right? So the top and the bottom are both circles. So I've got pi r squared on both the top and the bottom. So that's 2 pi r squared. And then I have the outside. Oh, I have a can right here. Okay, so I have the outside of this, right? Now, if I were to like chop this up, if I were to cut this and unfold it, what shape would that be?
Rectangle. Rectangle.
It would be a rectangle, right? If I slice this can right here, and then I cut off the top and the bottom and I unfolded it, I would have a rectangle, right? Now this side of the rectangle would be H, but this side is the side that was curved. Does anyone think they know what the length of that side would be? Or essentially the length of the outside of this? What would the length of that be?
Maybe
2 pi r.
2 pi r, it's the circumference, right? So if this is 2 pi r, the length of the circle times the height, because it's just an area of a rectangle really, if I unfolded that, I would get plus 2 pi r h. It is important that you can kind of visualize and think through those dimensions because they're not likely to give you those equations. Okay, we have 9 minutes of class left. I'm going to give you probably 7 to get started on this. I'll check in maybe at 5. Okay, I'm not giving you anything else. I gave you the equations. I didn't even tell you what's what. I didn't plug anything in, so you're going to probably need to do that. Make sure you know what we're trying to find. We're trying to find radius. We're told the volume is 512, and we want to find the minimum material used. And the minimum material used. So I'm going to send you to your small groups. If I can get this thing to open, come on. Come on, small groups, let's go. Where is that? There we go. All right, I'll see you in a few.